Hello, students. Welcome to part 2. You're going to learn about equations.
We are going to learn to write equations from tables and ordered pairs, which will be the same because a table is just a way of organizing the ordered pairs. Because the table is a better organizational depiction, we're going to start there. Now, we are going to look at an equation that has a constant rate of change. Okay? A constant rate of change can be found by looking at the way the inputs and the outputs change. We are going to write a ratio to describe how the output changes when the input changes. So it's always going to be the change in the y on top and the change in x on the bottom. Now look at the way the outputs are changing. Here it goes up by 1, up by 1, up by 1. So the outputs are changing by 1 when the inputs change by 1 or increase by 1. So since the inputs are changing by 1 too, we're going to put 1 on the bottom, and 1 divided by 1 is 1. This constant will then become the coefficient of x. So we'll write y equals, which is going to be our standard way of trying to write an equation here from a table, y equals 1x. Now, if you look, that's not necessarily true. Can you multiply 1 times x and get this? No. So add or subtract to adjust. 1, what would you have to do to 1, add or subtract to 1 to get -2? Well, 1 minus 3 is -2. Now check it for the rest. 1 times 2 is 2. Remember, that's where we got the coefficient. 1 times 2 is 2. And if we subtract 3, do we get -1? Yes. 1 times 3 is 3. And if we subtract 3, we get 0. And 1 times 4 is 4. And if we subtract 3, we get 1. So our equation is y equals 1x minus 3. Or we don't have to write the coefficient of 1, y equals x minus 3. So here's our equation that represents this table. Let's look at another example. Let's first look for a constant rate of change. Here we are adding 25. Here we added 24. Here we added 51. Does this look like a constant rate of change? No. Plus here we're adding 5. Here we're adding 2. And here we added 3. So there's no constant way that our table is changing. So we're going to use option 2 here and just look for some possible relationships between x and y. So what could we do to 0 to get 0? Well, we could multiply 0 by anything to get itself. So let's go to the next one. What could we do to 5 to get 20? Well, we could take 5 and add 20, and that would get us 25. We could take 5 and multiply by 5. That would give us 25. So you see how I'm listing some possible relationships? Now, let's see if either of these hold true for the rest of them, adding 20 or multiplying by 5. So if I take 7 and I add 20, do I get 49? No. But if I multiply by 5, do I get 49? No. So that means that neither of these possible relationships work. So now let's look for something totally different. Let's look at exponents, square roots, and absolute values. Now think about exponents. Is there some exponent that we could give 5 to equal 25? Yeah, 5 squared is 25. 5 times 5 is 25. 5 squared. Well, let's try that with 7. If we square 7, do we get 49? Yes, because 7 times 7 is 49. If we square 10, do we get 100? Yeah, because 10 times 10 is 100. So this equation says you have to take the input, or the x, and square it, and that's how you get the output. So this is y equals x squared. Let's look at another table. Let's first look for a constant rate of change. So here it's increasing by 2, increasing by 2, increasing by 2. When the inputs increase by 1, increase by 1, and increase by 1. So we do have a constant rate of change. The output changes, or the change in y, a triangle means change in y. The change in y is 2 every time the x changes 1, and 2 divided by 1 is 2. So 2 is going to be the coefficient of x, or y equals 2 times x. Now, take 2 times x and see if that gets you your output. 2 times 2 is 4, not 5. 2 times 3 is 6, not 7. 2 times 4 is 8, not 9. And 2 times 5 is 10, not 11. So you can see that every time when we multiply by 2, we're off by 1. So we have to add 1 to adjust our constant rate of change to match our outputs. So our equation is y equals 2x plus 1 more. Now, for a set of points, we will use the same steps. Why? Because a table organizes a set of points. So here you see a set of points: 1, -7, 2, -13, 3, -19, 4, -25, 5, -31. You can take this set of points and organize it into a table and then use the same steps you had before. Look for the constant rate of change. Here we're subtracting 6, subtract 6, subtract 6, subtract 6. So our change in the y, or the output, is -6 every time the input increases by 1. And -6 divided by 1 is -6. So this is going to become our coefficient of x. So we know that y is equal to -6 times x. If we take -6 times x, we get -6, -12, -18, -24, -30, and you can see that each time it's off by -1 more. So our equation is actually -6x minus 1 to adjust it to match the outputs. So our equation is y equals -6x minus 1. This can be done for any set of ordered pairs. Here's another set of ordered pairs. Just take the ordered pairs, rewrite them as a table because it allows you to see how the inputs and outputs change a little more easily. Here we can see that the outputs are changing by 1.5 every time. And every time our inputs increase by 1. So our change in the outputs is 1.5 when our inputs change 1. So our constant rate of change is 1.5, and that becomes the coefficient of x, so y equals 1.5x. Now, if you take x and multiply it by 1.5, 1.5 times 0 is 0, not 8. 1.5 times 1 is 1.5, not 9.5. 1.5 times 2 is 3, not 11. 1.5 times 3 is 4.5, not 12.5. And 1.5 times 4 is 6, not 14. So you can see that every time it has to increase by 8 more to match the outputs. So our equation is actually 1.5x, so multiply your x by 1.5, but then add 8 more. Now, occasionally your input-output chart does not have to increase the inputs by 1. So if you look at the outputs here, it's going up 6, up 6, up 6, but if you look at the inputs, it's going up 2, up 2, up 2. In other words, there's missing input and outputs. You can see that here in this one, the change in y was 6 when the change in x was 2, so the constant rate of change was 3, or it changed 3 every time the input increased by 1. So if we took these input outputs, here's the ones that were given in our table, and we added the inputs and outputs in between, we can see that it increases by 3 every time it increases by 1. Increases by 3 every time it increases by 1. Together, that's an increase of 6 every 2, just like in this input-output table. So now we can see that it increases by 6 every time it increases by 2, which is the same as increasing by 3 every time it increases by 1, which both divide down to 3. Now, that means that our coefficient of x is 3, so we have y equals 3x. But if you take 3 times x, you do not get the output. In any circumstance, if you only multiply by 3, your input would be 2 less than your output. So we have to add 2 more to adjust our constant rate of change to match the output. So our equation is y equals 3x plus 2. So let's summarize what we've learned. We've learned that an equation is a statement that two amounts are equal. We also learned that it defines one variable in terms of the other. We also learned that equations can contain constants, operations, and variables, kind of like expressions, but the difference is they must have an equal sign. We also learned to write equations for real-world situations, sets of points, and input-output tables by using these steps: reading the real-world situation, rereading the situation and marking the text for key operational words, constants, and unknown values, and using the markings to write an equation. We also learned that there are two options when we have sets of points in input-output tables, depending on if there is a constant rate of change or if there's no constant rate of change. If there is a constant rate of change, write a ratio to describe that constant rate of change, use that constant as the coefficient, and add or subtract to adjust. But if there's no constant rate of change, list some possible relationships for the sets of values, including exponents, absolute values, and square roots. Determine if the relationship works for all the values, and then write your equation.
Bye bye, kids.